So other than Lewis' systems, after he had come about, you will see multiple other logicians who have created their own axiomatic systems to describe modal logic. And one very interesting result is that simultaneously there were a group of logicians termed the constructivists who created an alternate system of logic that is different from classical logic, in which they underscored the importance of proofs, constructive proofs and direct proofs, and as such they created a new axiomatic system based on this. And we'll go on to see how Kurt Gödel managed to show that such a constructivist logic system can actually be mapped into a certain modal logic system. So let us first examine the foundations of intuitionistic logic and why, the justifications behind why we should adopt it. So imagine you're a king. You're a king who wants to build a bridge to cross a very rough river. You consult two people, one of which is a classical logician and the other is an intuitionist / constructivist. You want to know whether building this bridge is feasible, to know whether you should allocate resources and manpower to building it in your kingdom. So the classical logician will use the law of double negation. By using the law of double negation, he claims that since it is not impossible that the bridge is built, we can conceive of a possible world where this bridge exists. Because it is not impossible, you can rephrase it to not possible. And by the law of double negation, it means that it is possible that this bridge is built. Now, obviously, he's not wrong. He uses a very valid rule in classical logic and he uses it correctly. Just that it doesn't really prove anything. It's quite a useless statement. He's stating something that's not very consequential in your decision of whether to go ahead in building this bridge. On the other hand, the constructivist will have a different approach. Because of his emphasis on direct proofs, he will first list all the materials that he needs to build the bridge and he will come up with a well thought out plan. He will calculate all the engineering calculations needed for the blueprint or the mathematical considerations, and he may even come up with a model design for the bridge. And with his vast knowledge of physics, of engineering, of geometry, he will come up with a proof that there's a certain design that exists, a concrete design that this bridge can be built. So how does this analogy link back to the early 20th century? At that period of time, there was a rise of a certain group of logicians who felt that mathematical truths are not discovered but they are constructed. And therefore, if you have a mathematical statement, they do not have true values that are inherent to themselves. The true values of mathematical statements are not independent of our ability to construct a proof of them. So it can be summarized very well with this statement. To say something is true means we know it is true as a result of possessing a constructed example as a proof, as a direct proof. To them, to the constructivists, directly generating the actual object is more meaningful than simply asserting that it exists based on indirect reasoning or a line of indirect proofs. Let's examine a more mathematical example. This is a theorem in number theory. There exists irrational number a and b such that a to the power of b is rational. Irrational numbers are simply numbers that cannot be represented by a fraction, a finite fraction. This is a very beautiful and popular proof this is often introduced to students when they are learning introductory number theory because it shows them what mathematical reasoning is really capable of. So we just take two numbers a and b, both are the root of 2. We first start by knowing that the root of 2 is irrational. You can prove it by a lot of methods, which I won't explain because it's not really related to what we are doing here. So a to the b will be root 2 to the power of root 2. There are two cases for a to the b. So a to b, it can either be rational or irrational. If a to b is rational, we'll have our desired result. We would have proven that irrational numbers a and b can form a rational number when you raise one to the power of the other. So the first case is settled, proven. Now we move on to the second case. Let's say the case that a to the b is irrational. We will take a and b to be root 2 to the root 2 and root 2 respectively, because in this case a root 2 to the power of root 2 will be irrational, because that's the case we are considering. So when you raise these two irrational numbers to the power of each other, a to the b, you'll get something that can be simplified using the rules of indices into root 2 squared, which is 2, which is a rational number. So you have concluded this branch of the proof that raising an irrational to an irrational number can give you a rational number. So this branch is proven, and because both branches are proven, both possibilities are proven, you have proven that there's a possibility that a to the b is rational. You are not saying that root 2 to the power of root 2 is rational. You are saying that it is possible that it's rational, because you consider all the cases and say, well, it's a possibility that it's rational. There's a problem that constructivists see with this kind of proof, in that it doesn't really tell you much. It raises certain possibilities. It say, well, it can be like that, it can be like this, but it doesn't come up with a constructive example, with an exact example, with two specific numbers a and b, such that when they are raised, you form a rational number. Now let us move to a constructivist proof. U refers to the number a to the b. We can actually prove that root 2 to the power of root 2 is irrational. This is a constructivist proof. We can refer to a theorem in number theory, and you can perhaps prove the theorem, but it is not elementary and it is quite challenging mathematically to prove the theorem. But let's say you manage to prove it. Then by using the theorem on root 2 to the root 2, you realize that u is transcendental and all transcendental numbers are irrational. This is a result in algebraic theory, which we will not go through much, but this is simply an example of how a constructivist proof will be vis-a-vis a non-constructivist proof, as stated previously. Let us move now to the basics of intuitionistic logic and how you can quantify them by using axioms in logic, parallel to what we have done for classical logic. In intuitionistic logic, double negation doesn't hold. Law of the excluded middle, LEM, also doesn't hold, and indirect proof also doesn't hold. In fact, all three are very much related together. If one of the three does not hold, it means that the other two will not hold. Let us show how indirect proof is derived from double negation and LEM. In the process of indirect proofs, we are using the negation not P. We are saying that not P forms a contradiction, therefore not P is false, hence it is P. We are using a negation not P to show that we can derive P by a series of logical moves, and by the law of excluded middle, it is not P, which by double negation is P. This is the process of indirect proofs, and it uses both the LEM and double negation. LEM asserts that every proposition is either true or false, even if we cannot determine which. But then, according to constructivists, we can only claim that a proposition is true if and only if we can concretely, directly prove that it is. And that is the main reason and motivation behind them rejecting LEM. In fact, LEM and double negation are very connected. When I say I am not dumb, it simply means that my mental state occupies a state that is mutually exclusive to not dumb. And by double negation, such a state is a state where I am smart because not dumb. Sorry, it's a state that I am dumb because not dumb. It's a double negation. So from this line of reasoning, you can show that not dumb and dumb are mutually exclusive. And this is a statement behind LEM. It is not the case that not dumb and dumb. So you can easily derive LEM from double negation, and they both will imply each other. You can think of it as possibly a biconditional or an equivalence. Now to a more formal description. It's the Brouwer-Heyting-Kolmogorov interpretation of intuitionistic logic. The three mathematicians have come up with a series of axioms that really describe what logical operations mean in the context of intuitionistic logic. The first case is conjunction. For conjunction, you have to provide explicit evidence for both A and B by having two separate constructions for A and B. That's the definition by constructivism. Why not instead we define it as a proof that P and Q can hold simultaneously? I mean, my reasoning is that because in life, proofs are modular. Proofs of P and Q is modular. When you say I prove P and Q, it means that I can prove P and I can prove Q. I have two separate proofs of P and Q. I can use a proof of P for some other proofs, and at the same time I can also use a proof of Q for some other proof, because I can prove both P and Q. And therefore it's defined as a pair of proofs, as a pair of separated proofs. Let's move on to disjunction. Disjunction in the BHK interpretation is a bit more counterintuitive, because in classical logic, disjunction is inclusive. When you say P or Q, it means P or it means Q or it means P and Q. But then in the BHK interpretation, we have a more exclusive view of disjunction in terms of proofs. When we prove P or Q, we must specify which of the alternative is realized. Either P is realized or Q is realized. You must choose one of the tagged pairs, either A or B. You choose either a proof of P or a proof of Q. Thirdly, the definition of implication is formed in such a way that it implies a direct method to convert evidence of P into an evidence of Q. It's a function that maps P into Q. In terms of a proof, it maps the proof of P into the proof of Q. That's because in constructivism, Implication is not some abstract inference. It's not some unconnected thing that simply that's simply defined based on truth tables. Instead, it's a mathematical transformation. It's a direct link. You can apply mathematical operators to convert a proof of P into a proof of Q. In fact, this actually is somewhat related. Is related loosely to the Curry-Howard correspondence, which is the observed isomorphism between this BHK system and computing systems or type systems. You can map you can map implication in BHK into a function type in computing logic, which is simply a type that is assigned a function which receives an input and maps it to a specific output. That is how you can view implication in intuitionistic logic. Let's move on to number 4. Because constructivists reject the use of indirect proof that assumes not P and thereafter arrives at a contradiction, it asserts that we have to show not P. That in order to show not P, we must possess a function that converts any P into a proof of inconsistency. Without possessing this function, we don't have a proof that not P, because we no longer can use indirect proofs. So we must use a direct proof, and this is the definition of a direct proof. Lastly, you cannot prove absurdity. If you can prove absurdity, that means that any statements can be proven within the BHK system, because a statement is either absurd or not absurd. And by absurd, you basically refer to contradictory statements. If you can prove contradictory statements, then you can simply prove anything. You can prove that P and not P can hold simultaneously. Just because you reject the law of excluded middle, it doesn't mean that you can hold contradictory results in the BHK interpretation, because the BHK interpretation interprets truth values based on proofs, but it doesn't say that something can be true and false at the same time. And that is why you cannot prove absurdity, you cannot prove contradictory statements. There's a question that we may raise when we are looking at the definition of the BHK interpretation. Not P is defined as I can prove that there is no proof of P. But can I say that there is a proof that not P? The answer is no. I believe the main reason for making this distinction is that according to Gödel's incompleteness theorems, within any sufficiently strong system, there is a statement that cannot be proven but true. Gödel's statements will exist within any sufficiently strong axiomatic system. As such, just because not P, just because you can prove that there is no proof of P, that P cannot be proven, it doesn't mean that you can prove that you have proven that P is not the case as a result of Gödel's incompleteness theorems. Material implication. This is a bit more complicated. The interesting thing is that in classical logic, if P then Q will entail not P or Q. This is a result that can be proven in classical logic. But then in intuitionistic logic, this is not the case. but then the converse, meaning if you have this disjunction, it will entail if P then Q. So in intuitionistic logic, this is material implication is a weaker form of disjunction, but then in classical logic, it's equivalent. These two statements are equivalent in classical logic. Why is it so? Let's first take this statement. If P then Q, there exists a function f that converts a proof of P into a proof of Q. But this does not say anything about whether P can be proven or whether Q can be proven. So we cannot make this statement, because simply having this implication doesn't tell us whether you can prove any of this. However, let's say you have this statement. Either P cannot be proven or Q can be proven. In this case, if a formula for a proof of P exists, then we can prove that there is no proof of P. If a formula for proof of P exists, then we can prove that there is no proof of P. So Q can be proven, and this is consistent with the meaning of material implication. Therefore, the converse holds. Now let's move on to the more interesting part, which will be quite shortened, because it's quite complicated in terms of the actual rigorous proof, but I will just display how these three logicians have done it. Godel-McKinsley and Tarski. They took intuitionistic logic, they took the operators, the logical operations. They basically added a square box, the strong modal operator in front of each proposition. And for the more special types like implication, it's a bit different. For negation, it's also a bit different. For absurdity, it's the same. By doing this mapping from the BHK system, from intuitionistic logic, we will actually derive modal system S4. I will go into detail in the future what S4 modal system really entails and how does it differ from other systems of modal logic. But as of now, we just take it as it's a specific system of modal logic. This is a very important result, this translation. By proving that you can map intuitionistic logic into S4 modal system, it makes it easier to validate constructive proofs. Because we have modeled S4 quite extensively, we can model it both by using Kripke type relational semantics in terms of accessibility of worlds, which is simply in the form of a directional graph theory, or you can also model S4 using neighborhood semantics, using topological semantics, in which you make use of partially ordered sets to model modal systems. And because you have such a rich knowledge of modal logic and the S4 modal system, you can validate constructive proofs by having knowledge you have about the modal system, because you can map any constructive proof into logical statements within the S4 modal system. Another interesting thing is that it reconciles the radical departure of constructivism from classical logic by showing that it in fact is a form of classical modal logic. It's a form of logic that when you add modal operators, it becomes consistent. Let's move on to Lemmon systems. It's a very brief part. Basically, this logician created an alternate axiomatic system of modal logic by building it upon a base of propositional calculus. In 1957, he published a paper in which he took the propositional calculus base he added further rules, he added further axioms, and he formed a modal system. This differs quite a bit from Lewis systems because traditionally, Lewis, if you recall, defined axioms based on modal operation. Every single axiom defined contained modal operations in it. But then Lemmon showed that you can actually define a base of propositional calculus and then on top of it add rules to convert it into modal system. So it's a better visualization of how these two systems relate. So this symbol over here, it shows provability. If you see this symbol, it's a T but rotated to one side. It basically means that it is provable that something. You have got three propositional calculus axioms. If A is a tautology, then it's provable that A. The other one is uniform substitution. If you remember from Lewis systems, it means that you can substitute things of the same truth value and your resulting new logical statement will then have the same truth value. If A is the case and A implies B is the case, then so is B. This is modus ponens, essentially. It's a mode of inference. We then add further rules. These rules show how you translate classical logic into modal logic. It adds a few more criterion. It adds a necessity condition. All tautologies are necessary. Anything that can be proven in a system is necessary. It's a necessary truth. All axioms are necessary. And then he distributed the necessity symbol into an implication, and he also has substitution of strict equivalence. And if you recall from Lewis systems, the fourth rule essentially means that if you have got two different sentences flanked by a biconditional operator, it means that they are both equivalent and you can substitute them in any case and still yield the same result. He added more axioms. Axiom K, axiom T, this will be described in more details when we talk about modal systems. And he also added the transmission of truth values through an implication side, which also appeared within the Lewis systems. And that's all. That's the Lemmon systems. That's a Lemmon system. Not much of an attention has been put into it because it's quite elementary, I believe, and also because there's far more important stuff in modal logic that requires more of our attention, because this kind of things, it's a good discovery, but as we move on to more facets of modal logic, we realize more important things, more challenging things, and a much larger wealth of information which we will dive into in the future. And so we will stop the two alternate systems here, and just a little trailer for the next discussion. We are going to talk about how we can apply three-valued logic in attempting to describe modal logic. And interestingly, it failed. Applying three-value logic to describe modal logic failed, and we are going to examine why, and we are going to examine how you operate things, how you operate across the domain of logical sentences using three-value logic for our next video.